So we are on class 14. We're going to talk about approximating definite integrals today. You get your tests back. I just want to remind people, or maybe tell you for the first time, it's not officially written in the syllabus, but at the end of the semester, if it helps you, I do replace one low test grade with your final exam grade. So it's still worth it to go back. If you didn't do as well on this test as you would have liked, it's worth it to go back, make sure you know the material so that you can do well on the final exam, and then you can replace a low test grade with the final exam grade. Okay, so this semester we've learned many techniques for handling different types of integrals. But the fact of the matter is we still can't integrate most functions. Most functions are not in a nice enough form where u substitution or by parts or partial fractions or trig substitution will help us. So our techniques for approximating areas by using rectangles are pretty important. And then there are other shapes that we can use that will also give us even better approximations, and we're going to study them in this section. So some of this will be familiar because we have estimated areas under curves using rectangles before, but some of it will be a little bit new. Okay. So just to remind you, we're going to use left n and right n to denote the Riemann sums using n left and n right rectangles respectively. So I want to approximate the area from 1 to 3 under the curve f of x equals 3x squared using left 2 and right 2. So I have the graph copied twice here. So the area under the curve I can estimate with rectangles. So I just want the area from 1 to 3. So I'm looking at this interval here. So I want the area under the curve from 1 to 3, or I'm trying to estimate it. So if this one is going to be my left endpoint, this is going to be left rectangles, then I'm going to break it into 2 intervals. That's what the L2 means. Break your interval from 1 to 3 into 2 equal pieces. And then over each of those intervals, I'm going to build a rectangle, the height of which is the height of the curve at the left endpoint of the interval. So over my first interval from 1 to 2, I build a rectangle whose height is the height of the curve at the left endpoint. And then I do the same thing over the next interval from 2 to 3. I build a rectangle whose height is the height of the curve at the left endpoint. So that is estimating my area under the curve. It's not a very good estimate because I'm leaving a lot of area out, but let's write down how I would actually get this value. This first rectangle, its base is 1. And then what's its height? Half of 1? How do you get that? Oh, f of 1, yes. So we can write that down. 1 times f of 1. It's the height at the left endpoint. So f of 1, plugging 1 into the curve gives you the height of the curve at that point. And then my next rectangle, its base is 1. And its height would be f of what? All right, so now I'm just going to figure out what f of 1 and f of 2 are. So I have 1 times f of 1. If my function is 3x squared and you plug a 1 in there, you get a 3. Plug a 2 in there and you get 2 squared is 4 times 3 is 12. So that comes out to 15. All right, so now when I want to do right 2, again, I look at my interval from 1 to 3, break it into 2 equal pieces because I'm using 2 rectangles for right 2. But this time I'm going to determine the height of each rectangle by using the height of the curve at the right endpoint of the interval. So my first interval from 1 to 2, I go to the right endpoint at 2, go up to the curve, build a rectangle. And then for my next interval, go to the 3, up to the curve, build a rectangle. So those are the two rectangles I need to find the area of, add them together, and I'll have right 2. So this first one should be base of 1, height is f of 2. Second rectangle, the base is 1 and the height is f of 3. So this is 1 times 12 plus 1 times, if I plug a 3 into 3x squared, I get 27. So that comes out to 49. So I have a cute little geometer sketch pad thing here that we can check that these are correct, 15 and 49. So I'm just going to pull this up, and if I show the left, this is the curve y equals 3x squared. I'm going to show the left rectangles. It's going from 1 to 2.99999. So I got just about 26. Yep. I'm sorry, just about 15. Left sum is just about 15. Hide the left. I'll show the right rectangles, and I get just about 39. It's a little bit off because I couldn't get this 2.999 to be 3. All right. So we can use left rectangles and right rectangles. We already knew how to do that. So we're also going to learn how to use trapezoids today. So instead of rectangles over each interval, we're going to build a trapezoid over each interval. I'm going to use 2 trapezoids, same interval 1 to 3 here. Looking from 1 to 3. I still want to have 2 intervals. So I'm trying to evaluate trap 2, so 2 intervals. So I break it at 2 here. And instead of building a rectangle that has a height at either endpoint, I build a trapezoid where I connect the 2 endpoints at the height of the curve. So I go up to the height of the curve at both endpoints, and I connect them with a straight line. And I've created a trapezoid. Do the same thing on the 2 to 3 interval. Mark the height on the curve at each endpoint, connect them with a straight line. And these are 2 trapezoids that I want to get the area of, and that will approximate my area under the curve. All right, so quick hint, the area of a trapezoid where h is the height, which is, in our case, the width of each interval, right? Base 1 and base 2 are the 2 different heights of your trapezoid there, the 2 different bases of your trapezoid. And so the area is 1/2 height times base 1 plus base 2. So if I want to do trap 2 here, okay, my first trapezoid, I'm just going to use that formula, is 1/2 times the height of the trapezoid, which according to this picture is the width of my interval, in this case 1. And then base 1 plus base 2, that's this height plus this height. Okay, so this one is f of 1, and this one's f of 2. And then my next trapezoid, again using this formula, I have a 1/2. My height is the width of my interval, in this case 1. And then the 2 bases are determined by the height of the curve at the 2 endpoints. So f of 2 plus f of 3. And then I'll plug in some numbers for f of 1, f of 2, and f of 3 here. So this is 1/2 times f of 1 is 3, f of 2 is 12. 1/2, and then f of 2 is 12, and f of 3 is 27. All right, so this is 1/2 times 15 plus 1/2 times 39, which is 7.5 plus 19.5 27. All right, so I'm going to do a quick check on my geometry sketch pad. What does the trap rule look like? Show trapezoids, and I get just about 27, 26.979 there. All right, let's, before we jump to anything else, let's find out the actual area under this curve so that we can see what's the best here. So I'm just integrating from 1 to 3 of 3x squared dx. So how do I do this? Just take an antiderivative. What's the antiderivative of 3x squared? X cubed. Evaluated from 1 to 3. Plug in a 3, you get 27. Plug in a 1, you get 1. Exact area under this curve is 26. 26. Okay, so far we've gotten estimates of 15, 49, and 27, right? So 27 is clearly the best one so far. All right, so that's it for the demo. In the group activities, you're going to be discovering, doing some practice with left, right, and trap, and also discovering another rule called Simpson's rule.